these reactions. So do you have some predictions? Take a look at your notes. If you didn't get a chance to get through these on Tuesday, at the end of the class on Tuesday, write them, we'll take a couple minutes and try them again. We had a little more practice with this yesterday. So hopefully these are starting to look a little bit more familiar. Try to actually commit yourself to writing something down, even if you don't really know. Try to imagine you're taking a test and you have to write something down because you want to get partial credit. What would you write down? Write down some answers. It's a lot easier to figure out where you're going wrong if you have something to look at to critique. Write something down, right? Make some guesses as to what those products would be. All right, let's get some guesses here. So, of any of those three reactions, any one that you feel confident you know what's going on there? Yeah. Yeah, very good. The first one's an acid-base reaction. How'd you know?
Well, because it's H2SO4. So
Okay.
whenever you have an H, that's a hydro something.
Right. Yeah. So that's sulfuric acid. Yeah.
And when you have an OH, that's usually a
Yeah. So what does that tell you about the products then?
Well, it has to be water and
So we're going to make water as one of the products. Once we identify this as an acid-base reaction, then we can know that one of the products is water. And then the other product is the other combination of whatever other ions are there. So in this case, that's potassium and sulfate. All right. And then to balance that, like that. All right, any of the other two? Any idea what's going on in the other two? No ideas? Guesses? What's going on in these other two reactions? Can you tell what category they are in? Yeah, good. Second one is the gas evolution. How'd you know that? How'd you know the second one is the gas evolution?
It's a bisulfite reacting with acid.
Right, yeah. Yep. So we know this is gas evolution because we've got a bisulfite ion reacting with an acid, in this case acetic acid. So in those products then we know that ion breaks apart to form a gas, just like carbonates, the carbonates you used in lab yesterday broke apart to make carbon dioxide. The sulfites and bisulfites break apart to make sulfur dioxide. So our products are going to be sulfur dioxide gas and water, and then the remaining salt, which is sodium acetate. And I think that's just balanced as it is. It's gas evolution, yeah. So to determine or to look for a gas evolution reaction, you're looking for a couple different classes of ions, either sulfides, carbonates, bicarbonates, sulfites, bisulfites, or ammonium. So when you see those, then you look to see if they're reacting with an acid. Well, except for ammonium, if they're reacting with an acid. If they're reacting with an acid, then you can expect that it's going to form these gas evolution products. So, for example, what's going on here is bisulfite, HSO3, takes that hydrogen from the acetic acid and becomes H2SO3, which would be sulfurous acid. But that's not a stable compound. That doesn't just hang around like that. So it ends up breaking apart into SO2 and H2O. Just like H2CO3 carbonic acid breaks apart into CO2 and H2O. Yes, for that one, yeah. Sodium acetate. So that's the other salt that's produced. Yeah. All right. So for the last one, then, what's going on there? It's a precipitate. So we can look at we look at this and we see there's nothing like special here. There's none of those special ions that form gases. There's no acids and bases here. There's just regular old ionic compounds. So if you see regular old ionic compounds, chances are it's either a precipitation reaction or no reaction at all. So that's our guess here, is that it's one of those two. To figure that out, we switch the ions in the double replacement, so the cations go with the other anions. We've got here chromium 2 bromide and sodium carbonate. So we'll switch that and get sodium bromide and chromium 2 carbonate. So sodium bromide and chromium 2 carbonate. And then we have to use our magical powers of solubility determination to figure out if either of those things would be an insoluble precipitate. If so, then we have a precipitation reaction. If not, then there's just no reaction because all the ions are staying in solution. So are either one of those insoluble? Yeah, the chromium carbonate is. Carbonate is one of those ions that is almost always insoluble unless it's with an alkali metal. So that's going to be our solid precipitate, and then we just need to balance the equation. Okay, so now you know how to predict a bunch of different kinds of reactions, but it really just takes practice to see these over and over again and get used to these patterns. So as you're working through your homework, working through example problems, finding resources, just put as much time as you can into practicing these different types of reactions. The good news is that most chemical reactions are not really predictable, at least not at this level. So in order for them to be a predictable reaction, they kind of have to follow certain patterns. So once you get used to those patterns, there's not going to be anything really new that you'll see on a quiz or an exam, because patterns are patterns. All right. So we're going to skip the very last section of the book for now on oxidation reduction reactions. We'll get into that next week. So we can focus now on this idea of reaction amounts. You may have heard this fancy word, stoichiometry. Have you heard that word before? Maybe you heard it said in chemistry classes or whatever. Yeah, it just really means talking about like the numerical relationships, the amounts. Part of this we already know. One really important part of what we call stoichiometry is balancing equations. So let's quick practice that again. If you please, could you balance this equation where octane, which is the major component of gasoline, is combusted in oxygen? All right, see if you can balance that reaction, or that equation. All right, how's that balancing looking? Yeah? Okay. Let's take a look at it. So this is one where you have an even numbered alkane, and so you end up with that weird situation where you have to double them to get, otherwise there's odd numbers on one side, even numbers on the other side. So if we do that, that tells us that we need 18 waters, 16 carbon dioxides, and then we add up all those oxygens to get 50 on the right, so we need to put a 25 here. that what you got? Okay, great. So that's the first step of stoichiometry, because what do those numbers mean? What do those coefficients mean? Yeah, they're a molar ratio, or actually if we go all the way down to the molecule, they're a molecular ratio of how those have to react. So we could say, we could write these as a ratio, that in order to do this reaction, for every 2 moles of CH18, we need 25 moles of oxygen. Right? That's like what that's saying. That in order for this reaction to proceed fully, we need 25 divided by 2 times the amount of oxygen as octane. Of course, we can also write ratios as fractions. So another way to express this is like this, or its reciprocal. Right, something like that. So this many of this per this many of this. So it's a ratio. What happens, let's say this reaction is actually happening for real. We're burning some octane. What happens if we've got 2 moles of octane and 20 moles of oxygen instead of 25? What's the result of that? If you don't have that exact ratio. Let's say we had 20 oxygens instead of 25. What would happen to that reaction?
And not all of the octane reacts.
Yeah, not all of the octane would react, because we said, okay, for this to proceed fully, we need to have this ratio of 25 oxygens for every 2 octanes. So if we only had 20 oxygens, then there wouldn't be enough to react with all the octane, and so you'd have some octane left over. Or something else would happen, some other reaction would happen that could use less. But let's just say we have some left over for now. So that's what we're going to be talking about now, is how to deal with these situations where we may not have enough of one versus the other, and what does that mean, and how do we deal with that? So the way that the book gives this example is with pizza. So we'll also use that. Sorry if you're hungry. You can go get some pizza after class. Everybody familiar with pizza?
No.
What's that?
No.
No, we're not.
This is new. So pizza, we're gonna define a very simple pizza, a very basic pizza that is just cheese, sauce, and crust. All right. So let's say that our pizza reaction looks like this. You need 1 crust. You need 5 ounces of tomato sauce. And you need 2 cups of cheese. And that gets you 1 pizza. All right. So we can look at similar ratios to what we just talked about with octane and oxygen with our pizza. So what's the ratio between crust and cheese? What? Yeah, 1 to 2. So you need 1 crust. You need 2 cups of cheese for every 1 crust. So again, how many pizzas can you make if you have less than 2 cups of cheese? 0, like not a whole pizza, right? And we'll talk about fractional things in a bit. It makes a little more sense with molecules than it does with pizzas. But yeah, so you need that ratio. If you're lacking 1, you're not going to make that whole pizza. Let's go the other direction. What if we have extra stuff? So let's say we have 2 crusts, 5 ounces of tomato sauce, 2 cups of cheese. How many pizzas can we make? Still just 1, right? What if we have 3 crusts? 6 crusts? Still 1, because it's limited by the amount of the other reactants or the other ingredients that we have. So we need to maintain this ratio if we're going to make more pizzas. So there's a picture of some different examples here. from the book. So let's see. Whoops, maybe I went too far. Where's our pizzas? Here. All right. So if certain amounts of different ingredients have the possibility of making a certain amount of pizzas, but they're also going to then need more of the other ingredients. So if we had 4 crusts, actually, wait, I think I'm getting a little ahead of myself here. Let's talk about those. Let's talk about those specific ingredients. So what is it? 4, 10, and 15. So let's say we have 4 crusts, 10 ounces of tomato sauce. What did it say, 15? No, 15 ounces of tomato sauce. And 10 cups of cheese. How many pizzas can we make? So, how many pizzas can we make? What are you going with? 3. Why 3? Because what? That's how much sauce we have. So we look at how many pizzas we could make from each ingredient, and whichever is the lowest number, that's how many we can make, because that means we don't have as much of the other ones. So that's what that picture shows. So if we had 4 crusts, we could potentially make 4 pizzas if we had enough of everything else. If we had 10 cups of cheese, we could potentially make 5 pizzas if we had enough of everything else. If we had 15 ounces of tomato sauce, we could only make 3 pizzas if we have enough of everything else. So that means that the total number of pizzas we can actually make is 3, and then we're going to have leftover cheese and leftover crust. See how that works? All right. So that's kind of like the theory behind this. The thing that limits us is called the limiting reactant, the one that you have the least of relative to the others. Now notice relative to the others is important because we've got 15 ounces of tomato sauce. That's the biggest number. But that's still the limiting one because of the ratios of the other ingredients. So it's not whichever one you have the most of, it's whichever one you have the most of relative to the others, or whichever you can make the most product, or the least product from, is going to be the limiting reactant. Okay, so now let's talk about how to actually do this, like with calculations, and bring it back to molecules and equations. So, sorry, we're going to go back to this one more time. So when you decided that 15 ounces of tomato sauce is enough for 3 pizzas, how did you figure that out? How could you tell that 15 ounces of tomato sauce was enough for 3 pizzas? Go ahead.
We need 5 ounces for each pizza.
Yeah, so you used a ratio. The ratio was 5 ounces for each pizza. So 5 ounces per pizza, a 5-to-1 ratio. We've got 15 ounces of tomato sauce, so therefore 3 pizzas. Now you probably kind of did that in your head just looking at the numbers, because when the numbers are nice and even, we can do that. But when the numbers get a little bit trickier, maybe we can't. So if we go back up to our reaction here, we could ask that same question. Let's say, so the equation tells us that for every 2 moles of octane, we can make 16 moles of carbon dioxide, right? So let's say we have um, 3.5 moles of octane. And we have excess oxygen, so we just have plenty of oxygen, all the oxygen we need. We don't need to worry about how much oxygen there is. If we have 3.5 moles of octane and plenty of oxygen, how much CO2 can we make? All right. we're going to use that ratio in the same way. But because the numbers aren't so nice, we got 3.5 now. Our ratios are involving like a 2 and a 16. So it's not quite as easy as before. So when the numbers get a little trickier like that, it can be helpful to actually set up an equation to figure this out. So the way we would do this, or the way I would do it, if you have a different way that works, go for it. The key word there is works, though. So make sure that your way works. But what I would do is treat this like a conversion problem. We take 3.5 moles of C8H18, and we want to multiply that by a factor that tells us the relationship or the ratio between that C8H18 and the CO2 that we're being asked for. So if we set it up like a conversion, like we're converting moles of octane to moles of carbon dioxide, we're really just multiplying by a ratio, and we can get the numbers for that ratio straight from the equation. So the equation tells us 2 octane, 6 CO2. So we can put that right up here, or 16 CO2. 16 CO2 to 2 octane. And then we can evaluate that just like we evaluate any other problem like this. So we can go 3.5 times 16 divided by 2. And that tells us that we can make 28 moles of CO2. Try the same thing with the other product. How much water can we make? See if you can do that one. How much did you figure out? 30? 31.5? Sound good? Sound good? So what we can do is use the same idea, the same technique. No, maybe not. This recording the videos and writing all this stuff kind of like is all that this computer can handle. Whoa. Okay, close enough. So I'm still going to use that same starting value because that's the value that we're given. But instead of now looking for moles of CO2, we're looking for moles of the other product, water. And that equation tells us 18 waters, right? Okay, so same technique. And so in fact, if you are given just one value and you have a balanced equation, you can use these ratios to figure out what you need from anywhere else in the rest of the equation. All right, questions about that? So now let's see what happens in that in the situation where we don't actually have enough of one versus the other. find some numbers here. Let's look at another equation. I'll just give you the balanced equation this time. We're going to look at the synthesis of ammonia from nitrogen monoxide. To come back down to some smaller numbers. All right, so we've got NO plus water gives ammonia and, oh wait, that should be, I was like, why would we make, yeah, hydrogen, sorry, makes ammonia and water. Okay. So now let's look at the following situation. Let's say we have where are we here? .5 moles of NO. 8.2 moles of hydrogen. Okay? So we want to know what is the theoretical yield of ammonia. Now this idea of theoretical yield, that's the same thing that we just did in the previous problem. Theoretical yield is if this reaction went exactly perfectly the way that it should and every single molecule converted to a product, how much could you make? What is the most that you could possibly make? The reason it's theoretical is because chemistry doesn't work like that. You can never actually make perfectly 100% of what you expect to make. There's always stuff that's going on. There's equilibrium concerns where the reaction goes a little bit backwards. There's things happening in solution. Sometimes sometimes reactions just aren't efficient and they don't work right. So the actual yield that you get in the lab is never going to get all the way up to the theoretical yield, but the theoretical yield is what you could calculate for what you would expect to make. So we can say, what is the theoretical yield of ammonia? How much ammonia can we make? Now in the previous example, that was a little bit easier because we knew what number to start with. We could say, all right, we got 3.5 moles of octane. All we have to do is set up this ratio and then calculate the product based on that ratio. Now we're given amounts of both reactants. Why does that make it trickier? Why does having both reactants cause problems? Yeah, because you have to check both, just like with the pizzas. We don't know that those are given actually in the right ratio. We don't know that we have enough of both of them. One of them is probably going to be in excess, meaning there's extra, and the other one is going to be limiting, just like the sauce. So one's going to be like the sauce, one's going to be like the cheese, and we have to figure out which one's which. Because the numbers aren't as nice as our sauce and cheese, it's not immediately obvious by looking at it. I mean, maybe it is to you, but it's not necessarily immediately obvious. So we have to check it and see. So the best way to do that, and you'll find some different techniques as you practice through this. There's some different ways of doing it. There's some shortcuts that you'll probably get to eventually. But one way to just make sure that you get it right is to just do the thing with both quantities and see which one gives you less. So let's try that. Let's start with our 6.5 moles of NO and multiply it by that conversion factor that takes moles of NO and instead gives us ammonia. What numbers are that? What numbers should I use for that conversion factor? 2 and 2, because that's the numbers from the equation. All right, so that's easy enough. So for every 6.5 moles of NO, we should make 6.5 moles of NH3. It's always a good idea to look back at those numbers then and just make sure that that actually makes sense. And it does, because there's a 2 in front of each of them, so 2 of these should make 2 of these. That makes sense. Let's do the same thing with hydrogen. .2 moles of hydrogen times, and our factor now will have moles of hydrogen on the bottom, and again moles of NH3 on the top. And this time it's 2 to 5 because the equation tells us that for every 5 moles of hydrogen, we make 2 moles of ammonia. That one is less easy to calculate, so let's give it a try. Oops, 8.2 times 2 divided by 5 is 3.28. We'll say 3.3 because significant figures here, right? Okay, so what does that tell us then? What is the actual what is the theoretical yield? How many moles of ammonia can we make? 3.3. So this is the theoretical yield right there. Because we don't have enough hydrogen to make any more than that. So we can't make 6.5 moles, we can only make 3.3 moles. In this case, the NO is like the crusts, and the hydrogen is like the sauce. There's plenty of extra NO, plenty of extra crusts, but there's only enough sauce or hydrogen for 3.3 moles of ammonia. So we would say in this case that hydrogen is the limiting reactant and NO is an excess. There's extra. Okay, so next question, same reaction. If we decide that H2 is the limiting reactant and we have extra NO, how much NO would be left over? So for this question, I want you to talk about it in your groups. You're going to use similar techniques to what we just talked about. See if you can come up with a way to figure out how much NO would be left over in this situation.
When we're trying to look at two chemicals,
Yep.
I'm not sure which one's the limiting one.
Yep.
So whichever one gives us the lesser
Yes.
here is the limiting reactant.
Yes. Yeah, that's correct.
I didn't need to use the bathroom.
You figure it out? So how'd you do this one? How can you figure out how much NO is left at the end? How much extra? What do we need to know first to figure out how much extra? How much is used, right? So that's what we can figure out using the same technique. We can look at how much is used by doing that same exact type of calculation, just with a different ratio. So we know that our hydrogen is limiting, so we're going to start with that. And then this time we're going to figure out how much NO do we need for that particular quantity of hydrogen. So 8.2 times 2 divided by 5 is 3.38, just like before. So 3.3 moles of NO needed. Since we have 6.5, we just subtract that. And get that there would be 3.2 moles left. Is that what you got? All right. So that's pretty much all there is to these types of limiting reactant calculations. For any reaction, whether it's limiting or not, you use these molar ratios to figure out how much of one thing you need based on the amount of something else. If you're given both quantities of reactants, you always have to check whether one is limiting. Notice when I asked the question, I just asked, what is the theoretical yield? I didn't say, find the limiting reactant first, find this first. Like, I didn't give you any clues that one of them would be limiting. I just said, find the theoretical yield. Anytime you have that situation where you're given both quantities of reactants, and it doesn't just say, like, one is in excess, you have to assume that there might be a limiting reactant you have to check. All right. Let's extend this now to masses. So all of this works based on moles because chemicals react. The equations tell us that things are associated by counting. We need 2 of these for 6 of these, or 3 of these for 5 of these, whatever. But in reality, when we do this in the lab, we need to do this in quantities, like masses, maybe volumes of concentration, which I don't know if we'll get to that today, maybe. In the next chapter, we're going to talk about quantities of gases. So we're never actually going to weigh out a number of moles. We're going to weigh out a number of grams. So the technique is the same, but we may need to add an extra term on either side to convert between moles and grams. And what's the quantity we use to convert between moles and grams? How do you figure out, the molar mass is how you'd figure out the moles of something from grams or the grams from moles. So let's look at that same equation. I'm going to give you the same type of problem. The only difference is, man, this computer really does not like this selecting thing. No, I should have just redrawn it. Okay, I guess we're not doing that. I will just rewrite it for you. So we've got 2NO plus 5H2 Okay. So now the quantities I'm going to give you are going to be in grams instead of moles. All right, so same question. Find the theoretical yield. But this time we also want the theoretical yield in grams, because when we actually do the equation or do the reaction in the lab, we're going to weigh out our product and see how much we've got. Okay, so we know how to do that molar ratio. That all the things we just talked about still apply here. The only difference is we need to convert from grams to moles to be able to do that ratio, and then we need to convert again from moles to grams. So we're still going to have to figure out which one's limiting. So let's do that first. And we're going to actually just add that extra term right into the conversion. I think most people find that to be the easiest way to do it, rather than to do a bunch of consecutive steps. But if you prefer doing it in separate steps, that's fine too. All right, so what we're going to do here is we're going to take one of these quantities, like let's say grams of NO. We're going to convert it to moles of NO, then use the equation to figure out our theoretical yield based on NO, and then convert that also to grams. And then we're going to do the same thing with hydrogen because we don't know which one is limiting. All right, so we're going to have a like 4-term conversion thing here, and we should get grams at the end. And then we're going to make our decisions based on limiting reactant in the same way that we did before. So here's how that would look. I'll do one, and then you can do the other one. 86.3 grams NO. We're going to convert from grams of NO to moles of NO. Then from moles of NO to moles of NH3. And then finally, from moles of NH3 to grams of NH3. And so our final product our final answer should be in grams of NH3. Now that all our units are set up, we just need to put in the numbers. So the molar mass of NO is going to be, let's see, how many significant figures we got here? 3. So we'll say 14.01 plus 16.00, which is 30.01. So 30.01 grams per mole. Then we're going to use those same numbers from the equation, 2 to 2, that we did before. And then the molar mass of ammonia is going to be 17.03 grams per mole, which we can calculate from the numbers there. If we can get all these numbers, what is it? 86.3. All right, so we start with 86.3 divided by 30.01 times 17.03. Gives us 48.9, or we'll say 49.0 grams of ammonia. Okay, so that's our theoretical yield for ammonia based on 86.3 grams of NO. Now see if you can do the same thing and figure out the theoretical yield for ammonia based on hydrogen instead. So you're still going to use a very similar equation, make a couple changes to it as appropriate, and do the same calculation for hydrogen. right, you get it? What'd you come up with? So if we start with 25.6 grams of hydrogen instead, and we do all this, what do we end up for a theoretical yield of ammonia? Anybody get it? 87? 86? 87? Is that what you got? How about three significant figures? What is it? 86.3? Is that what you got? Okay, that's fine. For our purposes for now, that's fine. I'm just going to say 86.3. All right, so then which one is limiting in this situation? The NO is limiting because we make less of the product from the NO. Right? And we can answer the second question that we did before also. If we wanted to know how much hydrogen in grams was left over, we could do that. We could do that as well. Right? Same idea. We just have an extra factor on either side, converting from moles to grams. Okay. Everybody feel sort of okay with this so far? Sort of okay? Okay, great. We're going to practice this more in the discussion period too. All right, so a couple things before we move on to the next technique. So sometimes masses are given in kilograms or milligrams, right? Do you have to convert to grams to do this technique in those cases? Well, yes and no. You always can, and that's fine. But you can save yourself a little bit of work if you want your answer in the same units as you have your original numbers, then you don't actually need to. If you did the same equation, but you started with kilograms and you ended with kilograms, nothing else would change. You'd actually still get the same answer. The reason for that is the middle term, instead of being moles, would be kilomoles. But that would be fine. So if you're given a mass in kilograms and you want to do this type of thing, you could go kilograms to kilomoles of whatever the first reactant is, and then kilomoles of B, and then kilograms of B. And the same thing with milligrams. If you started with the milligrams of A, you could do a conversion to millimoles of A, get the factors from the equation millimoles of B, and then get milligrams of B. As long as you're staying in the same realm, whether it's the milli realm, the grams realm, or the kilo, or whatever realm, as long as everything's staying in that same place, you can use all the same numbers. You don't have to do those conversions. In fact, in lab, especially in organic chemistry, if you go on to do organic chemistry, you'll almost always be using milligram and millimole quantities. So you'll be reporting moles most often as millimoles instead of moles, just because of practically what you're using in the lab. So you can try that in your homework when you get those types of problems also. All right, the last thing we're going to do with respect to this stuff is solution concentration and stoichiometry. So like yesterday, often our reactants are not solids that we're weighing out by grams, but rather they're solutions. So there's stuff that's already been dissolved in water or some other solvent, and then you use that. So we have to know how much of that to use, just like we would know how much of something else. If you, for instance, you want to make a precipitate reaction, and you want to know what's the theoretical yield of precipitate, how much precipitate could you actually make? Well, you need to know how much of the aqueous reactants you're using. Right? So to do that, we're going to use a solution concentration measurement called molarity. And you've probably heard of molarity before. Molarity is defined as moles of solute divided by liters of solution, or per 1 liter of solution. So if we have a 0.250 molar solution of NaCl, what that means is that in that solution, there are 0.250 moles of NaCl per liter of solution. Notice, not a tricky thing, but something that sometimes gets forgotten about molarity is that the denominator is the total solution, not the solvent. So the way you make a solution like this is not to measure out however many grams of sodium chloride and then a liter of water and put them together. That won't be right, just like you figured out in the density lab. You need the total volume of a liter. So what you would do is take your 0.25 moles of sodium chloride, whatever that ends up being in grams, you put it in a volumetric flask, and then you fill it up to the 1 liter mark of water, and that makes sure you have 1 liter of solution. You can also use smaller quantities, of course. All right. So what we're going to do with this is basically two things. One is looking at like dilution and how do we change the concentration, and then second, how do we use this in our stoichiometric calculations? So for example, let me give you another reaction to look at here. This time, it's an aqueous precipitation reaction. So we've got aqueous potassium chloride reacting with aqueous lead nitrate. I think we saw this one before. Giving a lead 2 chloride precipitate. And then our spectator ions, potassium nitrate. Okay, so there's our balanced equation. Now, if we were to actually do this reaction, we wouldn't measure out some mass of KCl and some mass of lead nitrate to react these. We have aqueous solutions. So we're going to react volumes of a given concentration of aqueous solutions. So that means we have to do our calculations based on those numbers instead. So we have let me reword this a second. What volume in liters of a 0.150 molar KCl solution will completely react with 0.150 liters of a 0.175 molar lead 2 nitrate solution. All right. So that sounds like a lot going on here. But we can actually solve this in a similar way to what we did with the other stoichiometry calculations. The only difference here is instead of going from grams to moles and then moles to grams, we're going from liters to moles and then moles to liters at the end, because our solutions are liquids that we're measuring by volume instead of solids that we're measuring by mass. So our basic unit plan here is going to be, we're given liters of this KCl solution, or whoops, not the KCl, the other one. we're given liters of the lead nitrate solution. We're going to convert that to moles of lead nitrate. Then we're going to use our reaction stoichiometry to get moles of KCl. And then figure out how many liters of KCl solution that would be. So the technique here, what we're doing, is exactly the same as before. The only difference is how we get moles and then how we get our final amount in volume instead of mass. Okay, so let's look at how we can use molarities to do a conversion like this. Remember, we're going to follow our units. Always follow the units. The units are given. We want to go liters of this to moles of this to moles of that to liters of that. So that looks like this. 0.150 liters of lead 2 nitrate. And now we need a quantity that gets us from liters to moles. All right, that's our conversion that we want, from liters to moles. Well, if you look at that, that's actually the exact definition of molarity, moles per liter. Okay. And the molarity is given, so we can use that molarity as a conversion factor. The molarity of the lead nitrate solution is 0.175 molar, which means that that solution will have 0.175 moles for every liter. So in that way, concentration can work as a conversion factor. Our next term is exactly what we did before, using the coefficients from the equation to figure out how much of one reactant we need based on the other. In this case, we're going from lead 2 nitrate to KCl. So we're going to use our numbers from the equation, which are 2 and 1. Just like that. And then our last term, again following the units, is to go from moles of KCl to liters of solution. Now, once again, we have a term that is moles and liters. And the conversion factor that we can use there, or the ratio that we can use there, is the concentration, the molarity of the other reactant. So the molarity of KCl in the question is given as 0.150 molar. So that's 0.150 moles per liter. This time the factor is flipped because, again, we're following the units. So we want to cancel moles and have liters. If we follow the units, we always keep everything in the right side. All right, calculating all that through, 0.150 times 0.175 times 2 divided by 0.150 gives us 0.350. And this is an important type of a calculation if you want to do a reaction like this. If you know you have a certain quantity, if you have 150 milliliters of this solution, and you want to know how much of this other solution will react with it, this is exactly what you do. All right, how do you feel about that? Maybe, okay? Again, that's why we spent so much time looking at the molar ratios and doing everything with moles, because any other stuff that we need to throw in there is just a matter of how we get to moles and then how we get out of moles. The only actual new skill here is using the molar ratios to figure out what's limiting and what's in excess. Okay, the very last thing then for today is dilutions. Dilutions are easy. there's a simple equation that you probably have heard of before that makes everything nice and simple. You can say this equation in a couple different ways. I will stick to how the book does it, which is M1V1 equals M2V2. Have you seen that before? Have you seen that equation before? So this tells you the molarity of some solution, we'll call it solution 1, times the volume of solution 1 is equal to the molarity times the volume of the diluted solution. So if you dilute a solution, that means you're taking some smaller amount of a more concentrated solution and you're adding water to it to make a more dilute solution. The reason this works is because molarity is moles per liter and volume is liters. So we're multiplying moles per liter times liters and we get moles. When you're diluting a solution, you're not changing the number of moles. You're only changing the amount of water. So you're changing the concentration, but you're not changing the moles, and that's why this equation works. So the way that we use this usually is in these types of problems. What volume of a 6 molar sodium nitrate solution should you use to make 0.525 liters of a 1.2 molar solution. Okay. So we're taking a more concentrated solution, a 6 molar solution, where there's 6 moles per liter, and we're adding water until there's only 1.2 moles per liter, but we only want to make 0.525 liters of it. All right, so this is as simple as identifying what's going on here and then solving for the missing piece. In this case, this is our M1, our starting concentration. Oh, sorry. This is M2, our final concentration. And then this is the amount that we want at the end. So that's our V2. All right, so then we just set up the equation. 6 molar times V1 equals 1.2 molar times V2 So that tells us we need wait, that can't be right, hold on. Hit something wrong here. 1.2 times 0.525 is 0.63 divided by 6. Okay. Knew I did something wrong there. 0.105 liters. So we need about 105 milliliters of that more concentrated solution. You put that in a volumetric flask, fill it up to 525 milliliters, and then you've got your diluted solution that's exactly 1.20 molar. All right, so that's how dilutions work. Okay, that is it. I will see you downstairs in 15 minutes.